Okay, so we need to calculate the pH of a buffer consisting of 0.45 molar of hypochlorous acid and 0.62 molar of sodium hypochlorite. So we're given the Ka over there. So what we're going to do first is to write the reaction equation. So we're going to have a weak acid. So remember, to have a buffer, we must have a weak acid and its conjugate base. So what you're looking at here is this guy is a weak acid and that guy is its conjugate base. So HClO is going to lose hydrogen. So when it loses hydrogen, it's going to become this guy. So when you look here, we have sodium in front of that guy. So remember, sodium does not take part in this whole reaction. It's more like a spectator ion. So we just look at that guy. You see, it lost a hydrogen atom, and now it is that guy over there. So we're going to write the expression. So this is HClO aqueous plus H2O liquid, reversible reaction, and now we write that guy, sodium hypochlorite, and this is aqueous plus H3O. So what we have to do here is to write, to draw the reaction table and input everything that we have. So we're going to do this. So initial, change, and equilibrium. So initially we have 0.45 molar for our HClO. So we have 0.45, nothing for water, and we have 0.62 there, and we have 0 for hydronium ion. So we have, for our change, we have minus x, nothing for water, plus x, and plus x over there. And for our equilibrium concentrations, we have 0.45, that's 0.45 minus x, nothing for water, 0.62 plus x, and x over there. So now what we have to do here is to write our Ka expression. So the Ka expression is going to be like this. So I'm just going to say 2.9 multiplied by 10 to the power of -8 is equal to the concentration of ClO minus H3O plus divided by the concentration of HClO. So remember, I'm not including that sodium into my equation. So now I can input everything that I have into this equation. So now I have 2.9 multiplied by 10 to the power of -8 is equal to the concentration of that guy, which is 0.62 plus x, and the concentration of hydronium ion, x, and then divided by the concentration of my weak acid, which is 0.45 minus x. So what I'm going to do here is to solve for x. So I'm just going to multiply both sides by the denominator, and I will get something like this. And from there I can take everything to the other side, and then I will have something like this: x squared plus 0.62x plus 2.9 multiplied by 10 to the power of negative 8x and minus 1.3 multiplied by 10 to the power of negative 8. Now from there I can just add those two together and put all of that into my calculator and solve for x, and I get x is equal to 2.1 multiplied by 10 to the power of negative 8 molar. So our answer is in molar. So what we have to do now is to substitute that into these equations right here, the equilibrium concentrations. And remember, x that we found is this guy, the x for hydronium ion. And remember, what we do, we need to calculate the pH of a buffer solution. So we're going to use this guy x to find the pH. So we're going to say the pH is equal to negative log of multiply of the concentration of the hydronium ion. So that is the concentration of the hydronium ion. So pH is equal to negative log of 2.1 multiplied by 10 to the power of negative 8. So I'm just going to put that into my calculator, and we get a pH of 7.68. Now let's say that the question says we have to calculate the pOH. So if we want to find the pOH of the buffer solution, so already we have the pH of a buffer solution. So here's what we're gonna do. So we're gonna say 14 is equal to the pH plus the value of the pOH. So we already have the pH, so we can substitute that. So we have 0.68 plus the pOH. So we can take that to the other side and say 14 minus 7.68, and then we get the pOH of a buffer solution to be 6.32. But that is the final answer that we were looking for.